All right, today's trapezoidal rule. With trapezoidal rule, instead of approximating area by using rectangles, that's what we've done so far. We've done LRAM, we've done RRAM, and we've done middle RAM. Okay, we're going to approximate the area using trapezoids. You will see that trapezoids hug the curve a little bit better, and overall, you will see that it'll get you a little bit better approximation. All of them are approximations. Okay, there's a lot of different ways of approximating it. This is another way. The best way is to use our calculator and not approximate. But if we don't know what's happening, using this data will help us. Okay, so here's a picture. All we're doing on this first one is drawing trapezoidal rule. Okay, so we're going to draw a trapezoidal sum of 4 equal subintervals representing the area under the curve from 1 to 9. So we are going from 1 to 9. We're doing 4 equal subintervals. So how far apart is each one going to be? 2, because I'm really spanning 8, right? Because I'm going from 1 to 9. I'm spanning 8. I'm spreading them up into 4 subintervals. So I'm going to draw these lines. Notice that I'm not drawing all the way to the top. I'm just going to draw to the curve, down from 3, and then down from 5 from the curve, down from 7 from the curve, and down the 9 from the curve. Okay, because we're doing a little bit different here. But cool, I've now split up my graph. It's got 4 different parts. There's 1, 2, 3, 4. All of them are 2 across. All right, so from our first one, we are drawing a trapezoid. So a trapezoid is, all we're going to do is we're going to take the 2 different heights here, and we're going to connect them from one side to the other. Okay, instead of LRAM, RRAM, MRAM, where we just draw a straight line, this line can be slanted. This first one just kind of looks straight, but it's a little bit slanted. There's my first one from 1 to 9. My second one is going to be from 3 to 5, so I'm going to draw a line from the height at 3 to the height at 5. There's my second trapezoid. You can see this time, doing a trapezoidal sum makes it way closer. If I would just do an LRAM or an RRAM, it would be quite a bit off. But because we're doing trapezoid and averaging the 2 heights, it's going to be a little bit better. Okay, our next one goes from 5, from right here to 7. So it's that one right there. And then our last one is going to go from 7 until 9. So that one, not a great approximation from 7 to 9, but you get to see the same kind of concept. There is my trapezoidal rule. Not perfect. Okay, there are some places like right here where I have a whole lot of extra data. Okay, a whole lot of stuff that's not approximating, but you can see at times it can be a pretty good approximation, like from 3 to 7. Okay, and it just matters. The smaller your intervals, the better it's always going to be. Everybody make sense with how this works? Remember, to find the area of a trapezoid, you average the 2 heights. So you take the 2 heights, you divide by 2, and you multiply that by the base. That's what we did on Friday. Okay, that's how you find the average of a trapezoid. So average the 2 heights, and then multiply by the base. Okay, let's do that down below. So example number 1 here, we're going from -1 to 3 of x squared plus 1 dx. Okay, so this is what's being graphed over here. We are going from -1 until 3. We're doing 4 equal subintervals. So if I'm going from -1 to 3 and I'm doing 4 subintervals, how often am I going to make my lines? Every 1. So I'm going from -1, 0, 1, 2, and 3. There's my setup. We would like to know how tall each one of those lines are. Now, this equation is pretty easy, but if we weren't sure, we've got an equation right here. Okay, x squared plus 1. So if I plug in -1, how tall is this one right here? It's at 2. If I plug in 0, it's 1. If I plug in 1, I'm at 2. If I plug in 2, I'm at 5 because it's 2 squared plus 1. I plug in 3, I'm at 10. Make sense? Now we're going to find the area of the trapezoids. So my first one, I'm going in between these 2 lines, in between -1 and 0. So trapezoid 1, you don't have to actually write this out normally. I'm just doing it the first time. Trapezoid number 1. What's the width of our first trapezoid going to be? I'm going from -1 to 0. The width is 1, okay, because I'm going from -1 to 0. Okay, I'm taking that width times the average of the two heights. So the two heights that I have here are 2 and 1. So I'm going to go 2 plus 1 divided by 2. From 2 to 1, and I'm going to divide it by 2. That's going to tell me the average of these two heights. And that will tell me the area of this rectangle right here, or that trapezoid, sorry. What's the area of that trapezoid going to be? 1.5. 2 plus 1 is 3. Cut in half is 2. Or cut in half is 1.5. That's trapezoid number 1. Let's look at trapezoid number 2. We're going from 0 to 1. So my width is going to be 1 again. They're all 1 because we set it up to be equal subintervals. Okay? Then I'm averaging these two. I'm averaging these two dots to find that trapezoid. So between 1 and 2. So it's going to be 1 plus 2 divided by 2. I get 1.5. That's going to tell me the average of this trapezoid. Make sense on how this works? Find the other two for me, please. Trapezoid number 3, we're going from 1. The width is 1, and then we averaged these two heights. So the width was 1. I averaged 2 and 5, so 1 times 2 plus 5 divided by 2 gets me 3.5. If I'm doing trapezoid 4 here, Dev, what's the width of trapezoid number 4 going to be? It's 1. How do you find the height? 5 plus 10 over 2. He took the two heights, averaged them together, divide by 2. So 15 cut in half is 7.5. What is the actual answer going to be here? What do I need to do with all those numbers? Add them up. If I add them all up, you get 14. That 14 here, thumbs up if you think that's an over approximation. Thumbs down if you think that's an under approximation. Looking at that picture, you can see that while close, oh yeah, I'm a little bit above at least for each one. Pretty good approximation. Would you not agree with me there? It's pretty tight to that line for the most part, but this is an over approximation. In bell work, we talked about over-under approximation at LRAM, okay, and RRAM and all those good guys, okay, and we looked at whether it was increasing or decreasing. On this graph, am I increasing or decreasing? I'm both, but I'm always over-approximating. There's no place where I'm not over-approximating. So when we talk about trapezoidal rule, we don't care about being increasing or decreasing anymore. What do you think matters here when we're doing trapezoidal rule, whether I'm an over-approximation or an under-approximation? Concavity matters with trapezoidal rule. LRAM, RRAM, MRAM, increasing or decreasing. But trapezoidal rule, it's an over-approximation because trapezoidal rule and concave what here? What is this one? Concave up like a cup. When in doubt, graph it out. It's harder to see. Okay, when I just show you that picture, you'd be like, oh yeah, it's pretty close. But it is a little bit over the top. Makes sense on example 1. Let's keep going. For the most part, easy day. I'm going to go pretty rapid fire here because for the most part, it's pretty straightforward, but we'll get through what we need to get through here. Example number 2. The table shows the velocity in miles per hour of a truck at selected times using trapezoidal sum with 3 subintervals. What is the approximate distance the truck traveled from 0 to 3? Okay, so we're going from 0 to 3. We're doing 3 equal subintervals. So 1, 2, draw your hats on them. 3. Do 3 subintervals. Find the answer. Go. Subinterval. Vincent, what was your first one? 0.5. It's across 0.5. And what did you multiply by 0.5? 20 plus 60 over 2. He averaged his two heights. Cool, that's his first one. Okay, we're going to take that and we're going to add to that what? Here, Tyler, what's my second one going to look like? 1.5. Good, because 1.5 is the distance times? Good, 60 plus 40 over 2. He averaged those two heights. And then our third one here. Angela, what's my third one going to look like? 1, because I'm going from 2 to 3. 40 plus 30 divided by 2. Once you've done one, you've done a billion of these. They're not hard. Okay? Anybody actually type that into their calculator? What'd you get? 130. Let's talk about units here. It was velocity. Okay? We integrated from 0 to 3 of velocity dt. Okay? We approximated that to be this. It got us 130. It was in miles per hour, and we just did the integral of it. So what are my units going to be on this 130? Miles. And I'm going to do a couple lessons at once here, and we'll cover this again later. But this 130 miles is the change in position. It's the change in position. Or in other words, during that 3 hour span, you went 130 miles. Everybody agree with me on that? What if we would have said at t equals 0, your position was 20 miles from your house, or 20 miles past your house. You've gone 20 miles. You started 20 miles from it. Where are you now after 3 hours? 150. Dev, what'd you do to get 150? Added 20. That was his starting position. Okay, because at t equals 0, he was already 20 miles. He took 20 plus 130, and it got him 150. Does that make sense what we're saying there? We'll do that again later on. I'm just telling you now. Okay, one more here. We're going to go pretty quick. Oh, let's not even do it. Let's just set it up. It asks us to find the average temperature of this turkey. Okay, what is our units here? What did they give us? Degrees Celsius, and they want us to find the average temperature. They gave us temperature, and they want the average temperature. If I gave you test scores and wanted your average test score, what would you do with your test scores? Add them up and divide. So if I want to know the average temperature, I'm going to add them up from 0 to 30 of our formula, of our temperature. That will not tell you the average temperature. What are you going to have to do with that to find the average temperature? Times by 1 over 30. Because the span from 0 to 30 is 30. Okay, it's 30 minutes. That's what we're finding the average, or what we're going to divide by there. Okay, be careful with it. I know it's a little bit weird. Okay, again, not something I'm doing today. I will cover that again in a later unit. I'm just showing you right now. Okay, try that last one. Left Riemann sum, a right Riemann sum, and a trapezoidal sum are used to approximate the area under the curve from 0 to 1. Using the same subintervals. Which of the following would give you an underestimate? Talk with your neighbor and go. Show me with your fingers. 1 for A, 2 for B, 3 for C, 4 for D. What you get? Seeing lots of 4s. Let's see if that's true. Okay, left sum. If I'm doing a left Riemann sum, I've got a graph, so this is easy. I'm just drawing it out. So I'm going to touch from the left and go over. If I touch from the left and go over, am I in under approximation? Yeah. And if left sum is an under, we know that right sum is going to be over, okay, because this graph is strictly increasing. But if I wasn't positive, I could draw it real quick. Go from the right side, from the right side, from the right side. Oh, yeah, definitely I have some extra on top. Okay, so good. This is good. Right sum is none. Trapezoidal sum. Draw 2 lines and then connect them. Draw 2 lines and then connect them. It gets kind of hard if you draw them close together. If I draw them maybe a little bit further apart, you can see, is it going to be an over or under approximation? Under like we thought. Because it's a trapezoid and I'm concave down, it's going to get me an under approximation. So which one do I want? 1 and 3.